So you've done average rate of change before. You did that quite a bit last year in honors pre-cal, where you found the average rate of change of something. Remember that the average rate of change is the change in whatever typically over a time period, but it doesn't have to be over a time period. It can be the average rate of change of y with respect to x, for example, right? And if it's a line, well, that's slope. Okay, so let's take a look at this problem. Find the average rate of change of f of x, where f of x is x cubed minus x over the interval from 1 to 3. So the average rate of change is going to be the change in f, so that'll be f at 3 minus f at 1 over 3 minus 1. So that's going to be 3 cubed minus 3 minus 1 cubed minus 1 all over 2. See, that's 24 minus 0 over 2 is 12. That's average rate of change, right? And y'all did that a fair bit last year, yes? That's one of the big things that in pre-cal they're like, let's do a bunch of those. Well, the reason why is because it applies to calculus. You know, knowing average rate of change in and of itself, it's okay, but it's primarily so that you can use it in calculus. So graphically, this is what average rate of change looks like. Did you guys do this also, or did you just calculate average rate of change?
We applied it a little bit, but not much.
Okay, so graphically what's happening is this. If you have a function, y is equal to f of x, and you find the point b f of b and the point a f of a, this distance is going to be f of b minus f of a. And this distance is going to be b minus a. And you're like, oh, okay, well, this is also delta y, the change in y, and this is also delta x, the change in x. And when you take the change in y over the change in x between 2 points, what are you finding? Yeah, you're finding the rate of change, which is a slope. So that's why this is just slope. It's just the slope of the line, and they call this the secant line. If you remember, or maybe you don't, from geometry, when you've got a circle and you've got a line that goes through it in 2 places, that line is said to be a secant line or is secant to the circle. It's been a while since you've done that, I know, but that's what this is. And that's what's going on here. This line is going through our graph at these 2 points. So the average rate of change is the slope of this secant line. They are the same thing. Okay? So, on to page 2. Here's what calculus is more interested in. In addition to knowing the average rate of change on an interval, we may also be interested in knowing the instantaneous rate of change at a specific point. Okay, that's a little more interesting. So, let's find the instantaneous rate of change of the parabola y equals x squared at the point 2, 4. Okay, and you immediately recognize that there's a problem. Whereas up here, we had 2 points so we could find the slope, right? In this case, we've only got 1 point. and you can't find the slope of a line if you've only got one point. So we need an additional point. Here's what I'm going to suggest that we use. For this point, x is equal to 2, right? Let's take another point. And we'd like it to be incredibly close to 2. Now, we could actually pick like 2.00001 or something like that. But what I'm going to say is, let's let x be equal to 2 plus h. And you may be going, why did you use h for that? Because I'm moving horizontally, right? If I'm moving in the x direction, I'm moving horizontally. That's where the h comes from. So if x was equal to 2 plus h, then y would be equal to 2 plus h squared, which would be 4 plus 4h plus h squared. All right, well, now I've got 2 points, although one of them is not real well defined. What I'm going to do is find out what happens when I do the average rate of change between these 2 points and then take the limit as h goes to 0, so that these points are no longer away from each other, but they're incredibly close to one another now. Okay? So the average rate of change is going to be 4 plus 4h plus h squared minus 4 over the change in the x-coordinates, 2 plus h minus 2. We can simplify that in both the numerator and denominator. In the numerator, the positive 4 at the beginning and the negative 4 at the end drop out, so we've got 4h plus h squared. And the denominator, the 2's add out to 0, so I just have h. And since there's only one term in the denominator, I can just do that as a division problem, right? 4h divided by h is 4, and h squared divided by h is h. That's the average rate of change. And I could use that to find the average rate of change between the 0.24 and the 0.39, or between the 0.24 and the 0.525. I could use it for anything. But to find the instantaneous rate of change, what I'm going to do is take the limit as h goes to 0 of the average rate of change. And that's just 4. The instantaneous rate of change of that parabola at the point 24 is indeed 4. Okay, we're going to go on, but we're going to come back to that idea in just a second. The instantaneous rate of change of a function is a point, should be at a point, is the slope of the line tangent to the function at that point, also known as the slope of the curve at that point. All right, so let me show you what that looks like. If I graph and let me change this just a little bit, I think, so that it's a little easier. And let's graph y equals x squared. So it looks like that, right? All right. And I'm going to rescale this. Let's not go quite so far left and right. Let's say we go from -3 to 3, and from -1 to 8. So it's not quite square anymore, but you get the idea. And we're interested in what's happening right here. So what we said is that the instantaneous rate of change at this point is 4. So that means if I was to graph a line through the point 2, 4 that had a slope of 4, it should be tangent to this graph. All right, so that'd be y is equal to, using point slope, the y is 4 plus the slope is 4 times x minus 2. You see how this looks very much like the tangent to a circle, again, back from geometry, where it just kind of skirted that one point? That's what's going on here at this point. It just barely touches it and then keeps going. Doesn't cross over at this point. It just skims right along there. One of the things that's interesting, though, is look what happens just right in here. Can you tell the difference between the line and the curve very well? Or at all, frankly? No. So what we sometimes say is that this is the slope of the tangent, but sometimes we just say it's the slope of the curve, because they really are the same thing. If you were to just keep zooming in on this point, real quickly you wouldn't be able to tell the curve from the line at all. Okay? So, the instantaneous rate of change of a function at a point is the slope of the line tangent to the function at that point. It's also known as the slope of the curve at that point. Because if the curve is nice and smooth, if you zoom in on it enough, it looks like a line. All right. So, let's formalize this a little bit. The slope of the curve, y equals f of x, at the point P, which has coordinates a, f of a, is the limit as h goes to 0. Again, it's h because we're letting the horizontal distance between the second point and our point go to 0, of f of a plus h minus f of a all over h, provided the limit exists. The tangent line to the curve at P is the line through P with this slope. All right. So let's see what we can do here. Let's let f of x be equal to 1 over x. Find the slope of the curve at x equals a. So, all right, the slope of the curve is given by this expression. So the slope at a is equal to the limit as h goes to 0 of, and I'm going to just write the general form, f of a plus h minus f of a all over. If you want to write a plus h minus a to remind you that this really is just slope, that's fine, but what's going to happen is the a's are always going to subtract and you're always just going to end up with h on bottom. So in this specific case, that'll be the limit as h goes to 0 of 1 over a plus h minus 1 over a all over h. And we've done some limits like this. Do you guys remember what we need to do to simplify this, because if we try and substitute in h as 0, we get 0 over 0, which isn't very helpful.
Plus, or multiply by,
We are going to multiply by a form of 1.
It'd be A over S.
I'm sorry? You're sort of on the right track. What we'd like to do is get rid of this complex fraction. So I'm going to multiply by both denominators. I'm going to multiply by a plus h and by a. And in order to be mathematically legal, I have to do that for both the numerator and the denominator. So this will be the limit as h goes to 0. When we multiply 1 over a plus h times a plus h, that's just 1. So I'm just left with a. Minus, when I multiply the 1 over a times a, that's just 1. So I'm left with a plus h. All over h times a plus h times a. On these problems, it's never a good idea to try and expand the denominator. What we really want is for something to cancel. So we'd like it to be in factored form. In the numerator, got then the limit as h goes to 0 of a minus a, well, that's 0, so I'm just left with a negative h over h times a plus h times a. And at any value of h other than 0, h divided by h is just 1. So now letting h go to 0, I've got negative 1 over a times a. So it's negative 1 over a squared.
Where did the H and the A plus H go?
In the numerator,
In the denominator.
Um,
Second to last.
they're still there, and I let h go to 0.
Oh, right, okay.
So when I let h go to 0, I just have a in that term, or in that factor, rather. So that's part A. That's the slope of the curve at x equals a. This gives me an equation that lets me find the slope at any value I want. So for part B, in order to write the equation of a line, I need two things. One of them is not the y-intercept. Students always want to tell me that. I'm like, don't have to have that. I need two things. I need a point and I need a slope. The point can be the y-intercept, but it doesn't have to be. So the point, well, at x is 2, f of 2 is a half. So the point is 2 comma 1/2. And the slope is going to be, well, negative 1 over 2 squared. It's negative 1/4.
Wait, where'd you get the,
I'm sorry?
no, I got it.
You got it? Okay. So the equation of the tangent line would be y is equal to 1/2 minus 1/4 times x minus 2. Just using the point slope equation. By the way, pretty much every calculus book ever written, when they write the answers in the back, they always change this into slope-intercept form. I hate it. Why would you change this? Is this an equation of the line? Yes, it is. So on the AP exam, they're perfectly happy and they sometimes do on free response ask you to write the equation of a tangent line. They're perfectly happy for you to leave it like this. Now, if you're wanting to check your answers with what they have, when you have the answers to the odds, I would bet money they've changed them all to slope-intercept form. So you'll have to change it so you can check it. No, distribute the negative 1/4 and then combine the like terms. If we were to do that, that'd be a half minus 1/4 x plus a half. So that'd be y is equal to negative 1/4 x plus 1. All right. Any other questions about that? Okay.